This is lesson 12.8, similar solids. Solids are similar if they have the same shape and their corresponding linear measures are proportional. So we've dealt with similar two-dimensional figures, now we're going to deal with similar three-dimensional figures. And most of these are set up very similarly to how we dealt with three-dimensional, with the exception of when we get to surface area and volume. So let's look at the first example. It just says to determine whether the pair of solids is similar. Well, we want to make sure that they have the same shape, and right here we'd see two pyramids. They both have the same shape for the base, so that part's okay. And then make sure their corresponding linear measures are proportional, which means that if I set up these two lengths in a proportion with these two lengths, the proportion should actually be equal. So, and remember with a proportion, it doesn't matter how you set up the first set of numbers, as long as the second set of numbers matches it. So we want to see if this is indeed equal to, let's see, that 50 is this length, that goes with the 6.25, so that will go on the top in the second one. And then 28 is this length, 3.5 is the one that goes with it. Okay, and remember to find out if these are actually equal, we can use cross products. So we'll multiply these two, 50 times 3.5, and you should get 175. And then we'll multiply these two, 28 times 6.25, and you should also get 175. So these do come out equal. So because the sides are, the linear measures are proportional, we would say yes, the solids are similar. So you're going to do something similar on the try it yourself problem. Pause the video, determine if those two solids are similar or not, and then when you're ready to check your answer, press play. Okay, for this one, when you check the cross products, you should have gotten two different numbers. So you would say no, the solids are not similar. Okay. Just as we did with two-dimensional figures, we can find missing measures if we know two solids are similar by writing and solving proportions. So that was mostly what we used proportions for, was to find a missing measurement. Let's look at example 2. Find the missing measure for the pair of similar solids. So this is telling us that these two solids are similar. We don't have to verify that now, but we want to find the missing measure. So we look at the measurements and we see this is the one we're missing. Well, we want to make sure we are going to pair this one up with the corresponding measurement in this solid. So if this is x, then the one that goes with it is 6. Now they're not congruent. I can't say that x must be 6. We just know that they're proportional to another pair of corresponding sides. So it doesn't matter if you use 1 and 0.8 or if you use 3 and 2.4. Let's go ahead and use 3 and 2.4. Now remember, however you set up the first two dictates how you'll set up the next two. So I can do 3 over 6 or I can do 6 over 3. It does not matter as long as the other pair corresponds to that. So let's do 3 over 6. So 3 over 6, 3 goes with 2.4, so 3 is on the top, 2.4 must be on the top. And 6 goes with x, so x will be in the denominator. Okay, and remember again with these we will use cross products to solve them. So here we have 3 times x is 3x equals 6 times 2.4, which is 14.4. And then, just like a regular equation, from here to get rid of the 3, we'll divide both sides by 3. And we get x is equal to 4.8. Now, it's always a good idea to make sure that this makes sense. Notice in this solid, the 6 was the longest side. Same thing here. If this is the correct length, this would be the longest side of this solid. So this does make sense with the figure. Okay, for the second try it yourself problem, you're going to do something similar with these two cones. So pause the video, find the missing measure, and when you're ready to check your answer, press play. Okay, for the missing measure here, you should have gotten x equals 20 inches. Okay, now here's where this gets a little bit more tricky. And you have seen in your recent assignments some relationships between surface area and between volume of two shapes where the sides have been doubled or tripled or things like that. So this will just generalize that, if you've already observed that, this will just generalize it to all shapes. So if two solids are similar with a scale factor of A over B, and you can also think of this as a ratio of A to B, then the surface areas have a ratio A over B squared, and the volumes have a ratio A over B cubed. So just to take a really simple example, this is telling you that if you doubled the dimensions of a solid, the surface area would not double, but it would multiply by 2 squared, or 4. And the volume also would not double, it would multiply by 2 cubed, or 8. So we have these two relationships here. Surface area of solid A over surface area of solid B is equal to A over B squared, or A squared over B squared. Same sort of idea with volume. Volume of solid A over volume of solid B is equal to A over B cubed, or A cubed over B cubed. Now this probably all sounds a little bit confusing, so at the top of the next page, we're going to look at a very basic example of two cubes that are obviously similar. Any cubes are similar. And just see what the relationship is between their surface areas and their volumes. So let's look at this first one. This is a cube with a side length of 2. Let's first figure out what the surface area of this cube is. So for a cube, you can always use the shortcut of s equals 6s squared. The surface area is 6 times the side length squared. So if the side length here is 2, 6 times 2 squared. And of course we'll do the exponent first. 2 squared is 4, times 6 is 24. And we'll talk about the volume in a minute. Let's first just focus on surface area. In this cube, we now have a side length of 3. So again, we'll use our shortcut, s equals 6s squared. And here the s is 3, so s equals 6 times 3 squared. And again, order of operations, 3 squared is 9, 6 times 9 is 54. Okay, so now I chose two numbers where it wasn't really easy to see what you multiplied one by to get the other, because that won't always be the case. So if we just look at surface area, these two have a ratio of 24 to 54. And if I were to reduce this, I could divide both of these by 6, and I would end up with 4 over 9. And this is completely reduced. Well, this is clearly not the same ratio as the side lengths, which have a ratio of 2 to 3. However, 4 is 2 squared, and 9 is 3 squared. And so right in there you see that ratio of 2 to 3. But the surface areas don't have a ratio of 2 to 3, they have a ratio of 2 squared to 3 squared, or a ratio of 4 to 9. So surface area does not have the same ratio as the side lengths itself. It has that same ratio squared. Now let's look at what we get for volume. Well, a cube can also be treated as a rectangular prism, so we can just use length times width times height. And the length and the width and the height are all the same, so this is just 2 times 2 times 2, which is 8. Same idea here for the volume. We have V equals length times width times height, and here the length, width, and height are all 3. So 3 times 3 times 3. And 3 times 3 times 3 is 27. So just like we did with surface area, let's see what we get for volume. See what sort of relationship they have. So the ratio of the small volume to the large volume is 8 to 27. Now we can't reduce this at all, but we see that 8 over 27 is not equal to 2 over 3. But 8 is 2 cubed, and 27 is 3 cubed. And again, just like with surface area, you see that 2 to 3 ratio show up in here, but the volumes don't have a ratio of 2 to 3, they have a ratio of 2 cubed to 3 cubed. Okay, so now what do we do with that to actually solve problems? Well, let's look at the first example, and this one will involve surface area and volume in one problem. Really, this is just 2 problems hidden in one, so normally you should only deal with one or the other in a single problem. But this one will touch on both of them. It says a triangular prism has a surface area of 240 square inches and a volume of 120 cubic inches. If the dimensions are reduced by a factor of 1/5, what are the surface area and volume of the new prism? Okay, so we're going to have to solve 2 problems here, the surface area and the volume. So let's look at surface area first. Okay, so we know from the little box at the bottom of the first page that there's a relationship between the surface area of the 2 prisms, and it has something to do with the ratio of the lengths of the sides. So the first thing I want you to notice is that the dimensions are being reduced by a factor of 1/5. That means that there's a ratio of 1 to 5 between the 2 prisms. We are looking for the new prism after the dimensions are reduced. So we need to make sure we know, are we looking for the smaller part, the smaller prism, or the larger prism? Well, the new one is after the dimensions are reduced, so we want to find the smaller one. So when we set up a proportion, we'll put the scale factor for the side lengths on this side, 1 to 5. And then because we know we're looking for surface area has the scale factor squared, so we want to make sure we square both of those. Alright, so since we're dealing with surface area, we will need the original surface area. And since the one we're looking for is the smaller one, that the x, what we're looking for, should go across from the smaller number. The surface area of the prism we know will go on the bottom. So now that might sound kind of confusing. Let's think about this. Just like these 2 cubes up here had a ratio of 2 to 3 for their linear measurements, their surface area had a ratio of 2 squared to 3 squared. The dimensions here have a ratio of 1 to 5, so their surface areas have a ratio of 1 squared to 5 squared. And these represent their surface areas. X for the smaller prism, 240 for the larger prism. Okay, now we can go ahead and solve this to find what x is. So again, we will use cross products. So here, we have 5 squared, which is 25, times x. That's 25x. And then here, we have 1 squared, which is 1, times 240, is 240. And then we'll finish solving this for x by dividing both sides by 25. We get x is equal to 240 divided by 25, which is 9.6. And since we were solving for surface area, and the original units were inches, this will be square inches. Okay, so that's surface area. Volume will be set up similarly, except this time we're going to be dealing with cubed instead of squared. So for volume, set up a similar proportion. We're still going to use the same ratio, 1 to 5, but now because we're talking about volume and not surface area, these will be 1 cubed and 5 cubed. Again, though, we want the new prism, which is after it was reduced, so that's the smaller volume, so we'll put the x across from the smaller number. And the original volume was 120 cubic inches, so that will go down here, 120. Alright, and now we will use cross products to solve. So here, we have 5 cubed, which is 125 times x, so that's 125x, equals, here we have 1 cubed, which is 1, times 120, is 120. And then to finish solving for x, we'll divide both sides by 125. We get x equals 120 divided by 125 is 0.96. And our original units were in inches, and this is volume, so this is inches cubed. Okay, there are two similar try-it-yourself problems at the bottom. One dealing with surface area, one dealing with volume. So one of them will be like the first part of example 3, the other one will be more like the second part of example 3. Remember though, whatever it tells you is going on with the dimensions, write that first as a ratio. So you'll see that in each of these, reduced by half and tripled. Make sure you write those as a ratio involving two numbers first. And then set up your ratios. Don't forget either squared or cubed, and then solve. So go ahead and pause the video, work through those two problems. When you're ready to check your answers, press play. Okay, for the first one, the surface area of the new prism should have been 32.5 square feet. And for the second one, the volume of the new cone should have been 5,425.92 cubic feet.